Good day, everyone. We are going to introduce basic concepts, matrices, vectors, identity, and inverse. Before that, let's introduce Ellipsa here. Ellipsa is in a shop. She is looking at box A priced at rupees 5 and box B priced at rupees 3. She wants to find the price of one pen and one pencil. She decides to take the contents of box B out of box A. Box B's price is known, and that allowed her to find the price of a pen as 2. She proceeded, now that she knew the price of a pen, to take the pen out of box B at rupees 3, which immediately gave Ellipsa the price of a pencil. Now let's proceed to actually looking at this in the form of a matrix. So to save some time, I've written the equations already in this paper here. So 2x1 plus x2 equal to 5, x1 plus x2 equal to 3. So this is equivalent to what we saw in the picture earlier. X1 is the price of a pen and x2 is the price of a pencil. So on the left side in box A, we see 2 pens and 1 pencil. So that is where this 2x1 plus x2 comes from. And similarly, the box B has 1 pen and 1 pencil, and that is where the second equation is coming from, x1 plus x2 equal to 3. So let us introduce a few variables. These are matrices also. Matrices have rows and columns. So X we are actually introducing as x1, x2, which is a row matrix, which is 2, 1. This means 2 rows and 1 column. That is also the order of a matrix. Y is 5, 3. This is the price of box A and box B. Box A and box B written in the form of a matrix, which is once again 2 cross 1. A is written as 2, 1, 1, 1 to write. So once we have introduced these variables, here we can write the problem as y equal to ax in the form of matrix operations. That is, the equation that is highlighted here, y equal to ax, is exactly equivalent to the two equations that are written at the top of the screen. So if we take these matrices, write them down and do the matrix multiplication operation, we will take one row at a time. The 2 and 1 are the row number 1. We will flip them over and multiply that with x1 and x2, add them up. That will give us the 2x plus x1 plus x2. That will be equal to 5. So this is a matrix way of representing the same equation. So the process of solving this problem and finding the price and the pencil can be written like this. And we have actually now introduced A inverse. We also need to introduce this identity matrix. Identity matrix is generally, a square matrix. The diagonal with the ones here is called the main diagonal or the primary diagonal. Identity matrices have 1 on their main or the primary diagonal. Their determinant is 1. So we will talk about determinant more later on, and the secondary diagonal and all the other cells will be zeros. Only the main diagonal has 1 there. And identity matrices can be used to also define our inverse matrix. Inverse matrix is a matrix which when multiplied with the original matrix gives us the identity matrix. A few more properties of identity matrix. If we take the identity matrix, multiply it to a vector like x here, we get the same matrix back. That is, we do identity multiplied to the matrix x, we get x back. We can actually take the identity and multiply that with the matrix A, like shown here, and we will get the matrix A back. The identity operation on the square matrix of the same order like A, that is, identity matrix here has 2 rows and 2 columns, and the matrix A here also has 2 rows, 2 columns. If that condition is met, the operation is commutative. So IA equal to A equal to A also. So this is how we have defined the inverse as well as the the identity matrices. So the operation of solving this problem can be looked at as finding the inverse. So let us actually go to finding an inverse. I'm going to make a claim that Ellipsa in the previous animation basically was working on finding the inverse. So what I have done here is written down the matrix A and the identity matrix side by side. We are going to use a, intuitive approach as one of the two ways in which to find the inverse. We will do row operations to both these matrices. So with the goal that we do a set of operations, we will do that now. It will become clear. We will get identity matrix on the left side and A inverse on the right side. So that is what we are going to do. So the goal here is to start from A, do a set of row operations. These are actually linear scaling and addition type of operations that we do. I have named the rows as row 1 and row 2. We cleverly pick A1 and A2 variables in such a manner that we will eventually reach the identity matrix. That is the process that we do. I think if I do it, it will become more clear. So for this particular matrix, we want to make the primary diagonal have ones. With that goal, I can do, if I look at 2 here, 1 here, the idea that I first get is row 1 equal to row 1 minus row 2. That is the first operation that I will do to this matrix now. So if I do that operation, I will do that on both the sides. So I get the first row like this. I will keep the second row as it is for now. This is step number 1. Let's go to step number 2. So step number 2, the good part is the primary diagonal is already having 1, 1. The secondary diagonal element in the second row first cell, that is having a 1, which we want to make it as a 0. So I will do the operation row 2 equal to row 2 minus row 1. So that will, I'll write down the row 2 first. 0, 1, minus 1 and 2. Now let me actually fill out the row 1. So we have actually reached the identity matrix by following this process. This happens to be a simple matrix. We were able to actually pick A1, A2, B1, B2 values like 1 or 0 and do that. It was simpler operations. If we have a little bit more complex operations, it may take more steps for us to do this operation and get to I. The claim here is that now we have the identity matrix. So actually identity matrix is there on the left side and we have the inverse matrix on the right side. 1, minus 1, minus 1, 2 is the inverse matrix. So we will also prove how basically we are concluding this is the inverse matrix. But before that, actually, let me take the equation from the previous page. X equal to A inverse Y should give us the X. And to recollect, Y is 5, 3. That is the price of box A and box B. So if I do that operation here, that is if I take 1, minus 1, minus 1, 2, and apply that to 5, 3. 5 minus 3 because 1 minus 1 here, that gives us 2. Minus 1, 2 here, that gives us minus 5 plus 6, 1. So we did get the same answer as before. 2 is the price of the pen and 1 is the price of the pencil. The doing that operation did get us the same result, but also let's actually get the intuition around why this operation worked. So each of these steps we are doing a transformation like this. So a set of equations like this can be written in the form of a matrix operation. Basically we are introducing this matrix A1, B1, A2, B2, and each step can be written like we are performing a matrix operation like this. So on both the sides, what we have actually done is picked cleverly chosen matrix. Let's actually name it A1 for step 1. E1 for step 1. So we applied E1 on both the sides. We did this matrix multiplication of E1 with A on the left side and E1 with I on the right side. Then on step 2, let's actually introduce another matrix E2. So in this particular case, we have arrived at this already converged to an identity matrix for us. So on the right side also we did the exact same operation. So applying the identity matrix, we gives us the same, that is this term that we see here is the same as E2 E1. And if we look at the form of E2 E1A, we know that A inverse A equal to identity. We already have identity here. We have a term here. So the remaining terms that we see here, that is E1, E2 must be A inverse, and that's exactly what we see on the right side. So that is why this process actually works. So we in the next set of sessions we will actually go look at various different matrices and deepen our intuition. There are diagonal matrices, rotation, symmetric, non-symmetrics, especially complex eigenvalues and eigenvectors. It is very interesting to see what happens. So that is what we will go into in the next set of sessions. Thank you.